Well, folks, I'm sure by now you've all heard the story of Gauss, but it's a story I like, so I'm going to tell it anyway. So, once upon a time, in elementary school far, far away, in a distant land we like to call Germany, there was a teacher who was really annoyed at his students. This teacher believed in the power of rote memorization over independent thinking, and also in the powers of making kids busy to get some quiet time for himself. So he informed his kids that it would be vital to their education and to his nap time for them to add up all the numbers from 1 to 100. The students began their task of working, and the teacher began his task of snoring. And meanwhile, little Gauss was starting to get bored. So he began to add the numbers in a different way. Starting from 1, Gauss started to add 1 and 100, writing down 101. Then he continued to 2 and added that with 99. Writing down 101 again. He realized that every single pair was going to add up to 101, all the way up to 50 plus 51. Then there were 50 101s that just had to be added together, and that's just 50 times 101, or 5050. Excited, he gave the teacher his answer, and the teacher was probably super annoyed to be awakened. And as a reward, over 200 years later, we rote memorized the sum of the first n numbers formula, the same way Gauss once had to rote memorize addition. Isn't the textbook industry great?
Thank you to the mysterious voice for that wonderful story. That story makes me wonder at the pattern that Gauss found. So let's look at that for a bit. Well, if we say that the numbers that Gauss had to add is actually a sequence, a plus one sort of sequence, then the common difference, which I'll call yaya, is 1. Then for the first pair of numbers that Gauss added together, 1 and 100, I'm adding the first term 1 and 0 yayas with the 1, and the first term 1 and 99 yayas with the 100. And then for the second pair, I'm adding the first term and 1 yaya with the first term and 98 yayas, and so on. And for each pair, I'm adding the first term twice and the yaya 99 times. So the total amount becomes the same each time. And this is a property of any sequence with a common difference, because we base it on the number of yayas, not any specific number. So any sequence with a common difference has the property that the sum of the pairs, if you keep taking the number at either end, the sum of the pairs will always be the same. So the total amount for any plus something or minus something sort of sequence is going to be the amount of pairs that you can make times the sum of each pair. The amount of pairs, since they're all pairs of 2, is just going to be half the amount of numbers. And the sum of the pairs is the first term plus the last term, or the second term plus the second last term, or the sum of the middle two terms. They're all the same. In mathematical notation, this is S sub n equals n over 2 times a1 plus an. And there's some cool properties of certain algebraic or plus sort of sequences that result from this. I'll link some in the description, but you should play around and try to find your own. But taking the sum of plus sort of sequences seems kind of intuitive. Just count how many times you plus. A harder looking question is whether we can take the sum of a time sort of sequence. If we have the sequence Freya plus Freya times r plus Freya times r squared, there doesn't seem to be a nice way to add this other than manually adding the terms. You can factor out Freya, but that's about it. Wait a second. The towers in our first video were timesy sequences, and we found the sum of those. What did we do then? Well, we halved the tower, but does halving always help? If I write the sequence 1/3, 1/9, 1/27, and 1 over 81, then halving it just gives us more gross-looking fractions. 1/6, 1/18, 1/54, 1 over 162. So, there's nothing special about the number 1/2 that makes sequences easy to sum. What made 1/2 work in the tower? We were able to make the sequence slightly different, but with a lot of the terms the same when we 1/2'd it. So we were able to cancel out a lot of the terms. Specifically, we turned the first term into the second term, and the second term into the third term, and so on. How do we do this on all time sort of sequences? Something like this may look familiar to you, or it may not. If it does, can you tell why these two topics are connected? And play around with that. What happens if the sequence is infinite. What about a sequence of sums of times these sequences? Can you find the sums of other sorts of sequences? Try those out. For now, that's all. See you next time.